Welcome to this video. This is a very simple exercise that we'll be doing today, two of them. The first one is you've got a point P which is at 40 centimeters to the right of a negative charge. Now the first thing to do is to calculate the magnitude of this electric field E and draw the vector in this point to scale. If we want to do this, it helps by taking out our triangle in this situation and just start by marking out both point P. For instance, we will start with this one at 0 and just draw the other one 4 centimeters away from this one. Now once we've done that, we can start guessing or start drawing the field vector in this case. Now the length of this field vector just is pretty random, to be honest, but it just helps to draw things to scale in this case. So we make this we have to do it the other way around. Point P is to the right of this one. And we've got our charge Q here. And our charge in this case is -4 microcoulomb in this case, so it's a negative charge. What is the consequence of that one being a negative charge? Well, that means that we have to draw our field vector towards it in this case. Right. Had it been a positive charge, you would have had to draw it in the opposite sense in this case. Right. Now, having done that, we're going to calculate how strong this field really is. Now, the equation to calculate this is fairly simple. You take Coulomb's constant K, in this case, you multiply that by the source, in this case Q. You can use source or whatever you want in this case. Just make sure that you use the net value of it, because it being positive or negative just has consequences for the sense of vector E. Not so much for the magnitude of it in this case. And you then divide this by the distance to it squared in this situation. Now one thing you have to take into account is Coulomb's constant is calculated or is determined by using the standard SI values of charge, meaning it is a certain amount of Coulomb, this is expressed in Coulomb, versus, in this case, the SI units of distance meter. If you get a questionnaire which mentions centimeter, you first have to make sure that this is put to meters, being 0.40 meters for the distance in this example. And microcoulomb is also times 10 to the -6th before you start calculating. Now I'm assuming you're able to do this yourself. I do want some of these exercises, once they're done, to be sent to me at the end of the day. Now, the second question is, how strong would the electric field be at 4.0 centimeters distance? Meaning, if you make the distance 10 times smaller in this case, you would end up somewhere here-ish. What will be the consequence of this one? Well, the numerical values don't change all that much. The only thing you're doing is you're making your distance 10 times smaller. Now, if you make your distance 10 times smaller, because it is inversely proportional to the squared value of your distance, you would end up with an electric field that is effectively 100 times stronger than the ones you've calculated in step A. You don't have to write everything down again, just applying common sense and going like, oh, if I look at this equation and make this number 10 times smaller, this number will become 100 times larger in this case, because they are inversely proportional. Right. A slightly more difficult exercise is this second one. Again, you're supposed to make this one for yourself. I'm not going to do everything holding your hand. However, I do want to help with a few things. You have 2 point charges on the same line and to the right of a point P. Charge 2 is at a distance twice that of charge 1. If we have to draw this, it means that if I take point P, it's to the furthest point to the left. This one would be charge 1, and this one would be charge 2, as of my setup in this case. Now, if I want to do this, it's always safer to just mark what's going on in these situations. Point P, this is charge 1 in this situation, and this is charge 2. Now, if we read the rest of this, let me just get this one out of the way for now. Charge 1 is a positive charge. Charge 2 is a negative one. Alright, so we'll just fill in that this one's positive and this one is negative in this case. And it has twice the magnitude of charge 1 in this case. So this one is twice as strong as the first charge. Draw vector E in this point, meaning point P, and calculate the total field, total field vector, if charge 1 is 5.0 nanocoulombs and it is 5.0 centimeters away from point P. Meaning you only get the actual information for this charge, but it doesn't matter because it's all in relationship to charge 2, so you can easily calculate those two. However, the tricky bit is having to draw the vectors in this case. Now, if charge 1, I'll just use a red color for this one, and I'll use a blue color for field vector 2 in this case. Charge 1 is a positive charge. It is fairly weak compared to charge 2. However, it is the closest to it. Meaning, if I want to draw the field vector for this one, you pick a random number. 2 centimeters, for instance, is just fine to do this. Because you're just trying to figure out what the ratios between the two are. Right. This would be the electric field caused by charge 1. It's pointed away from it because it is a positive charge. Charge 2, however, is a negative charge, meaning it is pointed towards the charge, the source charge. Meaning I'm going to have to draw a vector to the right this time around. However, I kind of want to get it to scale, and I want to do this by thinking ahead. Now, in this case, this charge is twice as strong as the first charge, meaning you would expect the vector to be twice as long, 4 centimeters. This isn't quite correct, however. Why? Because the distance is also increased as you get to charge 2, meaning it is not as simple as just making this one twice as long. What do we mean by that? I'm going to use the equation that I've used for my first exercise to show you this. I do make this one twice as big, but I also increase my distance by a value of 2. Technically, you have to put these two in between brackets, and because it is distance squared, this will end up by being, or this will mean that my field vector will become 4 times weaker because of the doubling of the distance, right? It is, however, slightly compensated by having twice the charge compared to charge 2. What do we end up with? It would be twice as long, so meaning 4 centimeters. However, due to the increase in distance, it becomes 4 times weaker than before. Meaning if I want to draw this to scale, this one would have to be just 1 centimeter as opposed to the 2 centimeters of my first one. This is the situation we end up with. Calculating how much it is, however, is something I leave up to you, and it should be fairly simple. It's just using these same equations that I used previously. You're better off doing it separately. And then at the end, once you've calculated the individual value for field vector 1 and the individual value for field vector 2, seeing as it's a simple setup wherein there's 2 vectors with the same orientation but an opposite sense, it means you have to just subtract those 2 values. Largest value minus smallest value. In this case, I'm just going to freehand this. This would be the total field vector that we have in point P. I leave the numbers up to you, should be fairly easy to do. And I will see you in next class.